So far in this chapter, we've learned that electromagnetic radiation is described by its frequency, its wavelength, and we can calculate the energy of photons of those pieces or wave chunks of electromagnetic radiation waves. This work in waves, lambda, nu, energy, gave us great background into the understanding of how electrons in atoms actually work. And it's tricky to describe because it's actually a piece that describes it in two ways at once. And so we'll look at historically how it was developed in this video, and then in the next video we'll go through the results of how that works. So there was a scientist named Niels Bohr, and after Ernst Rutherford described how there was a central part to the atom called a nucleus with protons in it, he came along and described how electrons would reside around or outside of the nucleus. And he said that they would be in orbits around the nucleus, and that they would be in set specific orbits, and that the distance or energy between these orbits is fixed, and each electron has to be in a particular orbit. It can't reside in this area in between. Now, Bohr's model was good, but it wasn't perfect. But it led to some really good understanding. One thing that he couldn't describe mathematically was that the electron would then be attracted to the nucleus, and eventually the electron would crash into the nucleus. And so that was a fault of the Bohr's model, but Bohr's model was actually really good at getting us along the way in describing how electrons needed to exist in certain discrete energy levels, and that energy is involved in the transition of electrons from one place to the another. And so Bohr was a good step. He said that these electrons had to be a certain distance away, and the place where the electrons were or existed is called an energy level, and if you needed to move these electrons somewhere, you needed to add energy to make those electrons move. And we still harbor those exact thoughts today in what's called the quantum mechanical model of the atom. Along came a guy named Werner Heisenberg. Werner Heisenberg said that we're kind of uncertain where this electron is. He had something called the uncertainty principle. And the reason that it was uncertain where this electron was because the electron wasn't just a particle. It turns out the electron wasn't just like a small little piece that you could actually pick up and move, but it was also like a wave. And so here's where the conflict comes in. Is the electron acting like a particle, or is the electron acting like something with frequency, wavelength, and an amount of energy? Well, it turns out that we describe it as both. And since we describe it as both, we are uncertain where the electron actually is. Well, mathematically, we can model how uncertain we are and give a probability of where the electron might be. And so electrons actually exist in a probability zone that can be mathematically described or graphed in 3 dimensions. And we can actually graph this spatial area of where electrons probably are as you move from the nucleus out further away. A famous scientist named Ernst Schrödinger actually put mathematics to this and described the probability zones of where electrons most likely are for a multi-electron atom. This, of course, has more than one solution or more than one answer. One of the answers he had was called a principal quantum number. The principal quantum number described the energy level of the electron, how far the electron was away from the nucleus or is away from the nucleus. And this is where the electron would reside or more than probably be. He also came up with these graphical representations of probability zones, or areas where the wave-particle dual nature of the electron probably exists. These are called orbitals. Not orbits, but orbitals. In our next video, we'll take a deep look at the results of this Schrödinger equation and this probability zone graphing or mapping by looking at quantum numbers, energy levels, and orbitals.